Welcome to the deep dive. Imagine for a moment, you're building this groundbreaking new application. It's designed to be lightning fast, highly scalable, all running beautifully in Kubernetes. You've got your web servers, your processing engines, everything neatly containerized, ready to go. But then something happens. Your database container restarts, maybe due to an update or, it gets rescheduled onto a different node. And when it comes back up, poof, all your user data, your critical transactions, everything just gone.
Oh yeah, it's a developer's worst nightmare, isn't it? That scenario, it just perfectly highlights the core challenge we're really talking about today. Containers are inherently ephemeral. I mean, they're designed to be disposable, right? To spin up and down really quickly.
Right.
And while that agility is fantastic for scaling stateless services, it becomes this huge problem for any application that needs to remember things, that needs state.
To be stateful, yeah.
Exactly. Without a good solution, you're basically running a high-stakes operation on, like, a whiteboard that gets wiped clean every few minutes.
Yeah.
You just can't keep critical info safe.
And that's precisely why today we're doing a deep dive into Kubernetes volumes. Our mission here is to unpack what they are, why they're absolutely critical for making sure your data stays safe, persistent, and shareable, and also how they actually work to turn those nimble, ephemeral containers into reliable data preserving units. We're going to look at the mechanics, sure, but also the strategic edge they give you in this whole cloud native world.
Okay, so let's unpack this core idea. At its heart, what is a Kubernetes volume? Well, it's basically a way to store and manage data so it persists beyond the life of just one container instance. Think of it like external storage,
Yeah.
separate from the container's own temporary file system.
That separation is absolutely key because, like you said, containers are temporary things. They can be created, destroyed, restarted anytime, often without much warning. So if your database files or your user uploads or, critical logs were inside that container,
They just vanish.
exactly, gone, poof. Volumes provide that essential external storage layer. They decouple your data from the application's runtime instance. Makes total sense. So, what are the, let's say, core superpowers that volumes bring? First up, obviously, persistence. The data survives, restarts, crashes, even rescheduling.
That's the big one.
Then abstraction cleverly hides the complexity of the underlying storage. Is it local disk, cloud storage, network storage? The container doesn't really need to know.
Right. It just sees a directory.
Which leads to mounting. Volumes are just mounted into containers as directories. It's kind of like plugging in an external hard drive, It lets the app read and write easily.
Yep, very familiar concept for apps.
And finally, the sheer variety of types. This is important. You've got things like emptyDir, which is temporary storage.
Good for cache, maybe sharing files within a pod temporarily.
Right, but the data is gone when the pod dies. You need to remember that.
Yeah.
Then there's hostPath for using storage directly on the node.
Useful sometimes, but risky. Ties the pod to that specific node.
Yeah, can mess with scheduling. And then the really important one for persistent data, persistent volume claim, or PVC. We'll definitely need to dig into that more, how it connects to persistent volume.
Definitely. That's where the robust long-term storage magic really happens.
And of course, you have cloud-specific ones too, like AWS EBS or Google Persistent Disk, offering managed storage.
Yeah, abstracting away even more of the infrastructure headache. And the key thing is how these different types enable so many critical use cases. It's not just config files. We're talking about saving real production database files, making sure logs stick around for audits or debugging.
Right.
And that sharing capability within a pod,
Yeah.
super powerful. You could have, say, a web server writing access logs and a separate log processing container reading those same logs from the shared volume, like in real time.
Ah, okay.
No.
That enables some neat patterns.
For sure. This flexibility lets you build quite sophisticated multi-container applications.
So we know containers are ephemeral, volumes give persistence. Why is this such a game changer? I mean, really, why can't we just, ignore volumes for most real-world stuff?
Well, the simple answer is, if you're building anything stateful, anything that needs to remember data between restarts, you just can't ignore them. I mean, I've debugged systems where data just vanished.
Yeah.
It's like trying to solve a puzzle when half the pieces keep disappearing.
Huh. Yeah, the disappearing puzzle pieces. I like that.
Without volumes, data inside a container's file system is just lost when it restarts or gets deleted. That makes running things like databases, message queues, even CMSs incredibly difficult, maybe impossible in a dynamic Kubernetes setup. Data persistence is, well, it's fundamental.
So beyond just stopping data loss, what other strategic advantages do volumes unlock? It feels like more than just a technical fix.
Oh, absolutely. Decoupling storage from containers. It's not
Hmm.
just about preventing loss. It fundamentally changes your operational agility. Think about it. Zero downtime upgrades become feasible. Scaling your app instances up or down. Easy. Migrating workloads between, say, different cloud regions. You can do that without messing with your critical data. That's the real strategic win.
Making apps truly cloud native and resilient, not just containerized.
Exactly. And this decoupling also brings flexibility across environments. You can use different storage backends, NFS, S3, Azure Blob, whatever, making deployments way more portable. On-prem, cloud, hybrid.
Right.
And as we touched on, data sharing within a pod becomes much simpler, which is crucial for many microservice designs.
I think that WordPress example really hits home. The code, yeah, put it in containers, scale it easily, but user uploads images, documents, the media library, and the database itself. They have to persist.
Absolutely demanded.
Volumes make sure those bits are preserved. Even if the WordPress pod crashes, restarts, gets moved to another node, your website stays up, data stays intact. That's just non-negotiable.
So we've covered the what and the why. Now let's pull back the curtain a bit. Let's dive into the how. How do these volumes actually work their magic inside Kubernetes? Okay, the basic flow is pretty logical. First, you define a volume right in your pod's configuration file. It's YAML usually. You specify the type there, like emptyDir for scratch space, or persistent volume claim if you need data to outlive the pod.
Got it. Define it in the pod spec.
Second, you mount the volume. You tell Kubernetes which container in the pod should get this volume and at what path, like app data or varlog. The application inside the container just sees that path as a regular directory. It reads, it writes, totally unaware of the magic underneath.
So it just looks like local storage to the app?
Pretty much, yeah. Third, the storage backend. This is where the volume definition connects to actual storage. We mentioned emptyDir uses the node's local disk or memory temporary.
Gone when the pod's gone.
Right. hostPath uses a specific directory on the node itself. Useful for node-level stuff, but remember, ties the pod to that node.
Yeah, less flexible.
And then, critically, the persistent volume claim, the PVC. This connects to something called a persistent volume, or PV, which is usually backed by more robust external storage. Think NFS, AWS EBS volumes, Google persistent disks, that kind of thing.
Okay, and that's where the real durable storage comes in, right? The PVC and PV combo. So what are these different pieces? Persistent volume claim, and I think you mentioned storage class. How do they work together?
Yeah, this is where Kubernetes gets really clever with storage abstraction. So first, the persistent volume, PV.
Okay.
Think of a PV as a piece of storage that exists in the cluster. It's independent of any specific pod. It's like a pre-provisioned disk an admin makes available. Maybe it's a 100 gigabit NFS share or a cloud disk. It's a cluster resource.
Okay, so the PV is the actual storage chunk.
Exactly. Then you have the persistent volume claim, PVC. This is a request for storage made by a user or an application, usually within a pod definition. Instead of asking for a specific PV, the pod makes a claim. I need 10 gigabits of fast SSD storage, for example.
Ah, so it's a request, not a direct link to the storage.
Right. Kubernetes then takes this PVC and tries to find a matching PV that can satisfy the request. This abstraction is crucial. Your app doesn't need to know the specific infrastructure details.
Neat. And the storage class?
The storage class defines the type of storage and the rules for provisioning it. You might have a fast SSD storage class pointing to high-performance cloud disks or a standard HDD one for cheaper, slower storage. Crucially, storage classes enable dynamic provisioning. Kubernetes can automatically create a PV when a PVC requests storage of that class without an admin manually creating every single PV.
Ah, dynamic provisioning. That sounds incredibly useful. Makes things much more flexible.
Hugely.
Okay, let's walk through that PostgreSQL example to tie it all together. Running a database in Kube. How do these PVs, PVCs, storage classes fit in?
Okay, so first, maybe your cluster admin sets up a storage class, let's call it PGSSD, configured to dynamically provision, say, AWS EBS volumes.
Then your PostgreSQL deployment. Well, the pod definition wouldn't ask for a specific EBS volume. Instead, it creates a persistent volume claim, a PVC. It asks for maybe 50 gigabytes of storage using that PGSSD storage class.
Makes sense.
Kubernetes sees the PVC, sees the storage class, and goes, aha, I need to create a 50 GB EBS volume. It provisions the persistent volume automatically.
Binds it to the claim.
Right, binds the PV to the PVC. Then your PostgreSQL pod starts up, and it just mounts that persistent volume claim as a volume at, say, varlib PostgreSQL data.
And the result? Seamless persistence.
Yeah.
PostgreSQL just writes its data files to varlib PostgreSQL data like it's a local directory. But that data is actually landing on that durable EBS volume. So if the pod restarts, crashes, gets rescheduled.
The data is safe. Still there on the EBS volume, ready for the new pod instance.
Yeah.
Exactly. Rock solid persistence, all thanks to that PVC storage class dance. Ultimately, if you need a simple way to think about it, volumes are kind of like rugged external hard drives for your containers. They let you store data safely, share it when needed, and connect to all sorts of storage systems, from simple node disks to complex cloud solutions. And connecting this to the bigger picture, volumes aren't just some technical detail. They're really the bedrock, the foundation for running robust, reliable, scalable, stateful applications in Kubernetes. They're what transform those ephemeral containers into these powerful data-preserving units. They make Kubernetes truly viable for almost any application, not just stateless ones.
Yeah, it really does highlight the cleverness in Kubernetes design, doesn't it? Abstracting away so much complexity to make developers' lives easier and applications way more resilient. This deep dive into volumes, I think it uncovers a really critical, maybe sometimes overlooked piece of the puzzle for anyone working in containerized environments. So thinking about all this, what stands out to you about just how essential data persistence has become in this whole cloud-native world? Maybe it makes you wonder, what other, maybe seemingly small components are actually holding these complex systems together? What else enables the capabilities we kind of take for granted now?